NASA just reviewed their latest data, and it quietly confirmed something unsettling. 3I Atlas is not fading the way a normal interstellar comet should. Its structure is reorganizing. Its activity is deepening. And key signals are becoming more consistent, not weaker. That raises a real scientific dispute. Is this object stabilizing or crossing into a more dangerous phase of change? If this analysis is useful, please like the video and subscribe. Now, let's begin. 3I Atlas did not trigger concern because it was bright, fast, or visually dramatic. In fact, at first glance, it looked ordinary. An interstellar comet passing through the solar system is rare. But its basic behavior is not mysterious. As it approaches the sun, heat builds. Ice turns into gas. Dust follows. Activity peaks, then slowly weakens as the object moves away. That sequence is so familiar that it forms the backbone of nearly every early model used to describe objects like this. The problem was that 3I Atlas refused to stay inside that sequence. From the earliest days of continuous observation, something subtle kept going wrong. Each new batch of data was expected to sharpen the picture. That is how science usually works. Early uncertainty gives way to clarity as measurements pile up. Instead, clarity never arrived. Updates did not confirm earlier conclusions. They shifted them, sometimes only slightly, sometimes enough to force entire assumptions to be set aside. This did not look like progress. It looked like replacement. At first, the differences seemed small enough to ignore. A change in viewing angle can stretch or compress a cloud of dust. Distance can affect how bright a comet appears. Instruments have limits. Every observer knows that early data can be messy. For a while, that explanation held. But then the same kinds of changes appeared again and again, in ways that were hard to dismiss. The variations were not random. They repeated. They carried shape. They showed timing. That is when the discomfort began to spread quietly through the analysis. The issue was not that 3I Atlas was active. Activity is expected. The issue was that its activity did not follow a single track. Instead of rising and then falling, it shifted modes. One pattern appeared, then weakened, only to be replaced by another that behaved differently. This happened more than once. Each time, the object seemed to reorganize how material was leaving its surface. That is not typical behavior once a comet has already passed its closest approach to the sun. In most cases, the story is simple. The outer layers warm first. Easy ice escapes. Dust lifts away. As those layers are exhausted, the comet settles down. What scientists saw here was something else. As some features faded, others sharpened. As some forms of activity weakened, new ones took their place. The object was not winding down. It was changing form. Inside technical summaries, the language shifted in response. Words that suggest noise or instability slowly gave way to words that suggest pattern, structure, consistency, repetition. Those terms are not chosen lightly. Structure implies direction. Consistency implies a source that remains active over time. Together, they point toward processes that are not limited to the surface. This is where disagreement naturally enters the picture. One interpretation says this is still normal behavior, just compressed in time. That the object is shedding layers faster than expected, but still following the same rules. Another interpretation is harder to accept. That 3I Atlas is exposing deeper material in stages, each one altering how the object behaves as a whole. The difference between those views matters, because one leads to predictability, and the other does not. A fading comet becomes easier to understand with time. An evolving object becomes harder. Evolution here does not mean growth or intention. It means internal change that builds rather than resolves. Heat does not stop at the surface. It moves inward. New pockets of material reach critical conditions. New flows open. Each change affects the next. Once that chain begins, the future stops being a smooth curve and becomes a branching path. This is why the timeline itself raised concern. Changes that normally take weeks appeared in days. Features that should blur became clearer. Behavior that should simplify became more layered. Instead of calming as it moved outward, 3I Atlas showed signs of organization. That reversal does not fit comfortably inside existing expectations. By this stage, the central question had shifted. It was no longer whether 3I Atlas was unusual. That much was obvious. The real question was whether scientists were still watching a familiar process play out faster than normal, or whether they were watching the early stages of something that does not repeat cleanly. The data did not provide a clear answer, but it did something else. It ruled out the simplest explanations. Because one conclusion was becoming difficult to avoid. 3I Atlas was not settling down as it left the inner solar system. It was rearranging itself, and if that was true, then whatever came next was not something already mapped out by past experience. It was something still unfolding. One observation at a time. What made the situation more divisive was not what the data said, but what the images seemed to show. As soon as new frames of 3I Atlas were released, many people focused on shape. The coma looked stretched in one set, tighter in another. Some images suggested a tail splitting or fading. Others made it look sharper, almost cleaner to the untrained eye. It felt like something obvious was happening. To scientists, it was not obvious at all. Images are powerful, but they are also deceptive. A single frame freezes a moment without context. Brightness depends on exposure. Shape depends on contrast. Small processing choices can make faint structures appear or disappear. This is why researchers rarely trust one image by itself. They compare sets taken hours apart. They layer wavelengths. They subtract background noise. Only then do patterns begin to matter. With 3I Atlas, those careful comparisons raised more questions than answers. Side by side, images taken less than a day apart did not behave the way experience suggested they should. Earlier frames showed an inner coma that looked loose and uneven, with material spreading out in a stretched form. Later frames did not just look brighter or dimmer. They looked organized. The same region appeared tighter, more defined, almost shaped. That change alone sparked disagreement. Was this just a viewing effect? Or was the flow of material itself changing? This is where public reaction and scientific caution began to pull in opposite directions. Some observers argued that the object was losing material and becoming simpler, even weaker. Others saw signs of structure and assumed something new was forming. Both reactions came from the same images. Neither could stand on images alone. That gap between appearance and measurement became one of the most important tensions in the story. When researchers compared data across different wavelengths, the conflict deepened. Light that traces fine dust told one story. Light that highlights gas told another. When those layers were stacked and aligned, they did not cancel each other out. They reinforced a surprising conclusion. The changes were not random flickers. They were coordinated. Features shifted together, not independently. That kind of coordination is rare unless something stable is driving it. This is why the phrase "compare everything" became central to the analysis. Yesterday versus today. One instrument versus another. Old models versus new measurements. Each comparison removed one easy explanation. Viewing angle could explain a little. Distance could explain a little. Noise could explain a little, but none of them could explain why multiple observatories, looking at different aspects of the same object, saw changes that lined up in time and shape. At this point, the debate was no longer about whether the images were misleading. It was about whether they were incomplete. An image might suggest loss or gain, but the data hinted at rearrangement. Material was not simply leaving and thinning out. It was being redirected. Flows were shifting. Regions near the core were behaving differently from one day to the next in ways that suggested internal control rather than surface chaos. That idea makes people uncomfortable because it challenges a basic expectation. Comets are supposed to become simpler as they lose material. Their behavior should smooth out, not grow more complex. Yet the visual record of 3I Atlas did not show simplification. It showed contrast sharpening in some regions even as others faded. That combination is hard to explain without invoking changes beneath the surface. This is where interpretation splits sharply. One side argues that this is still normal comet behavior pushed to an extreme by unusual composition. The other side sees warning signs of a deeper process unfolding. Neither view can be proven from images alone, but together, they frame the real problem. When pictures and models stop agreeing, it is usually because something important is missing from the assumptions. By the end of this phase, one thing was clear. Looking at 3I Atlas was no longer enough. It had to be measured, compared, and tracked as a system changing over time. The images were not lying, but they were not telling the whole story either. And whatever that missing piece was, it was beginning to shape every observation that followed. The moment that shifted the discussion came from a detail that was easy to miss at first. It did not appear as a dramatic outburst or a sudden flare. It showed up as a faint shape inside the inner coma, visible only after careful processing, when contrast was enhanced and background light was removed. A subtle curve began to stand out. It was not a straight jet and not a random smear. It bent, it wrapped, it traced a path that suggested rotation. What emerged was a spiral-like structure curling outward from near the nucleus. This was not something seen in a single image taken in isolation. It appeared when frames taken hours apart were aligned and compared. The curve held its form. It did not jump or dissolve. It slowly extended, feeding material into the main tail. For scientists who study comets, that kind of shape immediately narrows the list of explanations. A spiral in the coma is not just decoration. It is a signature. It usually means that material is being released from a fixed region on a rotating body. As the nucleus spins, the jet sweeps through space, drawing a curved pattern in the dust and gas around it. For that to happen, three things must be true at the same time. The rotation must be coherent, the vent must remain active over multiple rotations, and the flow must be strong enough to remain visible instead of breaking apart. What made this unsettling was the timing. 3I Atlas had not shown clear signs of stable rotation earlier. Its behavior looked uneven. Activity came and went, yet here was a structure that required order, appearing in less than a day. The inner coma went from looking loose and confused to showing a clear, repeatable form. That transition was too fast to ignore. There was also the question of scale. This was not a faint ripple far from the core. The spiral traced back close to the nucleus itself. That suggests the source was not a surface layer that had already been stripped away. It pointed to a vent that had recently opened and remained active long enough to carve a visible pattern. In simple terms, something new had turned on. Some argued that this could still be an illusion. Processing can reveal shapes that feel more solid than they really are, but the spiral held up across different datasets. When observers adjusted the methods, the curve did not vanish. It shifted slightly, but it stayed. That persistence matters. False features tend to break apart when conditions change. This one did not. The comparison to earlier images made the contrast even sharper. Just hours before, the same region showed a stretched, uneven glow with faint branching behind it. There was no clear order, no dominant curve. Then, in the newer data, the chaos gave way to structure. It looked less like noise and more like design. Not in an intentional sense, but in a physical one. This raised a deeper question. If a stable jet had formed, where did it come from? Jets do not appear without cause. They require material reaching a temperature where it can escape. They require pathways through the surface, and they require enough internal pressure to sustain flow. For an interstellar object encountering this environment for the first time, that combination is not guaranteed. The presence of the spiral suggested that 3I Atlas was not just reacting moment by moment, it was entering a phase where at least part of its behavior was controlled by a repeating internal process. That idea marked a turning point, because once repetition appears, prediction becomes possible. And when prediction becomes possible, failure becomes meaningful. If the spiral remained in future observations, it would confirm that a new, stable feature had locked in. If it vanished or shifted dramatically, it would suggest something even more unstable beneath the surface. Either outcome carried weight. The spiral was not just a shape, it was a test. While the spiral drew attention to shape, another dataset quietly reinforced the same message through timing. This came from the light curve, a simple record of how the object's brightness changes as it rotates. In most comets, the pattern is rough but readable. Brightness rises as active areas face the sun, then falls as they turn away. Over time, the curve may wobble, but it usually settles into a single rhythm. With 3I Atlas, that rhythm never fully settled. Earlier measurements already showed signs of strain. Peaks in brightness were uneven. The timing between them drifted slightly from one rotation to the next. This suggested that the object was not spinning in a perfectly stable way. That alone was not alarming. Many small bodies tumble or shift as jets push against them. What mattered was what appeared next. In the most recent data, a new feature emerged on top of the main rise and fall. It was smaller, but it repeated in each rotation cycle. After the main peak, a secondary bump appeared at nearly the same point in time. It did not wander. It did not fade in and out. It showed up again and again, like a second pulse layered inside the first. This kind of pattern usually points to a specific cause. It means that more than one region on the nucleus is contributing to the brightness in a regular way. One area dominates the overall signal. Another adds a smaller, but consistent contribution. Together, they create a layered curve. This is not something random noise can produce. Noise does not keep time. The appearance of this secondary pulse lined up closely with the emergence of the spiral structure. That connection mattered. A stable jet sweeping through space would naturally produce both effects. It would carve a curved pattern in the coma and add a repeating brightening as it rotated into view. Two different measurements, taken in different ways, were pointing toward the same conclusion. This raised another point of tension. If a new active region had turned on, it meant that the object's behavior was becoming more complex, not simpler. Each additional active area adds force. Each force alters rotation. Rotation changes how heat is distributed. That feedback loop can either settle into balance or spiral into instability. Some argued that the secondary bump was too small to matter. It did not dominate the light curve, but its consistency was the issue, not its size. Small, steady forces shape systems over time. A repeating push can change spin just as effectively as a sudden shove, especially when the object is already under stress. For an interstellar object that had never experienced this level of heating before, the timing was significant. The appearance of a new, stable signal after closest approach to the Sun suggested that deeper material was becoming involved. Surface layers should have already responded and faded. What was activating now was something that had been insulated until recently. By itself, the light curve could have been dismissed as odd but harmless. In combination with the spiral, it became harder to ignore. Shape and timing were telling the same story. 3I Atlas was not just fluctuating, it was developing layers of activity, each one adding structure to a system that was supposed to be winding down. While shape and timing pointed toward growing order, the strongest confirmation came from a source that does not rely on appearance at all. This came from spectra, the detailed breakdown of light that reveals what material is actually present around the object. Unlike images, spectra are not influenced by contrast or perspective. They do not care whether a feature looks sharp or diffuse. They respond only to composition. When scientists compared the newest spectral data with measurements taken just one day earlier, the change was not dramatic, but it was unmistakable. At first glance, overall activity looked steady. There was no sudden surge in gas output and no large jump in brightness. From a distance, 3I Atlas appeared calm, even restrained, but inside the spectral fingerprints, the balance had shifted again. Signals tied to lighter, more volatile ices weakened slightly. At the same time, lines associated with denser, harder to release materials became more pronounced. The way light scattered off dust also changed, showing a growing contribution from larger grains rather than fine powder. This pattern is important because comet activity usually follows a simple order. The easiest materials respond first. These are the ices that sit closest to the surface and require the least energy to escape. As they sublimate, they drag small dust particles with them. Once those layers are depleted, activity typically fades. Deeper material remains locked away, insulated by what is left above it. What the spectra showed here did not follow that script. Instead of a steady decline in all components, 3I Atlas showed a trade. As one group of materials weakened, another grew stronger. This kind of exchange usually means that heat has reached deeper layers. It suggests that energy absorbed earlier near the Sun is still moving inward, crossing thresholds one by one. Each threshold unlocks a new reservoir of material, different from what came before. These were not single-line changes that could be blamed on noise or calibration. The same trend appeared across multiple observations when scientists looked at separate datasets taken with different instruments. The message stayed consistent. Deeper components were becoming more visible. Earlier dominant signals continued to fade. This persistence made coincidence unlikely. The shift also helped explain why the coma had begun to change shape. Gas and dust released from deeper layers do not always behave like surface emissions. They can emerge through narrower pathways. They can carry larger particles. They can maintain direction longer before dispersing. That kind of flow is far more capable of carving structured features, like the spiral already seen near the nucleus. This reinforced the interpretation that new vents had opened below the outer shell. These vents were not just adding activity, they were changing its character. Each new opening altered the mix of gas and dust feeding the coma. As a result, the appearance shifted. The light curve gained structure, and the system as a whole became more organized rather than less. There is also a broader implication that makes scientists cautious. Material buried deep inside an interstellar object has never experienced sustained heating from a star like the Sun. Its physical properties are uncertain. It may fracture differently. It may trap gas more effectively before release. When it finally vents, it can do so unevenly and with more force than surface layers ever produced. This introduces risk alongside fascination. One interpretation says this is simply delayed response, a natural outcome of insulation and time. Another interpretation sees a compounding effect. As deeper layers activate, they do not replace surface activity cleanly. They stack on top of what is already happening. Each new contribution changes how pressure escapes and how force is applied to the nucleus. The spectral data did not shout this conclusion. It did not need to. In planetary science, steady trends often matter more than dramatic spikes. Day after day, the same shift appeared. 3I Atlas was no longer venting only what was easy to lose. It was beginning to reveal its interior. And once that door opens, the behavior of the object rarely returns to something simple or predictable. What tied all of these changes together was something that could not be seen directly. Heat, not the brief warming at the surface that fades as distance increases, but heat moving slowly inward, step by step, through a body that was never built to handle it. This process does not stop just because the object has passed its closest point to the Sun. Once energy is absorbed, it continues to travel, long after the surface appears to calm. A comet nucleus is not a solid rock. It is closer to a loose framework, filled with cracks, pores, and weakly bonded material. Heat does not flow through it evenly. Some regions warm quickly, others lag behind. This creates delays, sometimes long ones, between exposure and response. What happens at the surface today can trigger activity deep inside days or even weeks later. This is why timing matters so much. The changes now appearing in 3I Atlas are happening after the most intense solar heating has already passed. Under simple assumptions, activity should be declining. Instead, new features are emerging. That reversal strongly suggests that energy absorbed earlier is only now reaching deeper pockets of material. Those pockets were shielded before. They are not shielded anymore. Each pocket behaves differently. Some contain ice that turns into gas easily once it reaches a certain temperature. Others hold mixtures that resist change until a sharper threshold is crossed. When one of these thresholds is reached, the response is not gradual. A new vent opens, gas escapes, pressure builds, then releases. From the outside, this looks sudden, even though the process leading up to it was slow. This explains why activity in 3I Atlas has arrived in waves rather than as a single rise and fall. One layer responds, then quiets. Another follows. Each new response reshapes the object's behavior. New jets form. Existing ones weaken or change direction. The system never has time to settle before the next change arrives. Heat moving inward also explains why the activity is becoming more organized rather than more chaotic. When surface layers dominate, emissions tend to be messy. Material escapes wherever it can. As deeper pathways open, flow becomes more focused. Gas and dust are channeled through narrower routes, producing stronger, more directional jets. These jets are far more capable of shaping the coma and influencing rotation. There is an important detail here that often goes unnoticed. Heat does not spread evenly across the nucleus. Rotation, shape, and composition all matter. Some regions may remain cool while others warm rapidly. This uneven heating creates imbalance. One side of the object pushes harder than the other. Over time, those small imbalances add up. For an object that originated outside the solar system, This situation is especially unstable. 3I Atlas did not evolve under steady sunlight. Its internal structure was shaped in a much colder, darker environment. The materials inside it may respond to heat in unexpected ways. Cracks can propagate. Weak layers can collapse. New pathways can open without warning. This is why scientists are cautious about assuming that deeper activity will simply replace surface activity smoothly. More often, the two overlap. Old vents continue to operate while new ones turn on. Forces that once balanced begin to interfere with each other. Each new source of outgassing adds another push, another torque, another stress on a nucleus that is already changing. From a distance, this can look like steady behavior. Brightness may remain similar. The coma may not expand dramatically, but internally, the system is becoming more complex. Heat is still doing work. It is unlocking regions that have never been tested under these conditions. This is the core of the concern. The changes seen so far do not suggest that 3I Atlas is cooling off. They suggest that it is still in transition. Energy absorbed earlier is continuing to reshape the object from the inside out, and as long as that inward march of heat continues, new responses remain possible. All of this internal change would be interesting on its own, but it becomes far more serious when motion is added to the picture. This is where the discussion shifts from appearance and composition to trajectory. As 3I Atlas continued to be tracked, scientists fed its latest position data into orbit models. These models account not only for gravity, but also for small extra pushes caused by outgassing. For comets, this is known as non-gravitational force, and it acts like a weak engine attached to the nucleus. In many cases, this effect is messy. Jets turn on and off. Force change direction. The result is noise that makes predictions harder. Earlier in the encounter, 3I Atlas behaved that way. The extra push jumped around. One update would suggest a certain direction. The next would weaken or shift it. That fit with the idea of chaotic surface activity and uneven heating. The latest update changed that picture. When the newest observations were added, the non-gravitational force did not disappear. It did not spike either. Instead, it became more consistent. The magnitude stopped jumping wildly. The direction aligned more cleanly with what would be expected from a stable set of jets acting over time. This was the first period in which the extra push behaved less like noise and more like a system. That consistency is a double-edged signal. On one hand, it makes the object easier to model. Stable forces are easier to track than erratic ones. On the other hand, it implies that the jets producing those forces are themselves becoming stable. They are not flickering on and off. They are staying active long enough to leave a measurable mark on the orbit. This lined up uncomfortably well with everything else. The spiral in the coma suggested a persistent jet. The light curve showed a repeating secondary pulse. The spectra pointed to deeper material feeding new vents. Now, the orbital data added another layer. The object was not just changing internally, it was beginning to behave like a coherent multi-jet engine. For a small, fragile nucleus, that is not automatically good news. Jets do more than push an object along its path. They also apply torque. When gas escapes from one side more than another, it changes how the nucleus spins. If jets are balanced, those effects can cancel out. If they are not, rotation can speed up, slow down, or shift in orientation. Over time, even small torques can accumulate. This is where the situation becomes delicate. 3I Atlas has already been through months of intense heating and cooling. That process stresses material. It opens cracks. It weakens bonds. Now, as deeper jets turn on and remain active, They apply sustained forces to a structure that may already be compromised. The more organized those jets become, the more consistent the stress they apply. Some might assume that stability is always safer than chaos. In mechanics, that is not always true. A random shove might jostle an object briefly. A steady push in the same direction can reshape it completely. If the spin state is still shifting while the jets are stabilizing, the forces do not average out. They stack. This is why the orbital update drew attention even without dramatic numbers attached to it. It marked a transition. 3I Atlas appeared to be moving from a phase dominated by short-lived outbursts to one dominated by sustained flow. That kind of transition changes how risk is evaluated. There is also an important timing issue. These stable non-gravitational forces appeared after new activity had already been identified in the coma and spectra. That suggests cause and effect. The jets responsible for shaping the spiral and adding structure to the light curve are likely the same ones now influencing the orbit. Separate observations were converging on the same physical drivers. For an interstellar object, this convergence matters even more. Its internal structure was not shaped by repeated passes near a star. It has no long history of gradual adjustment. Everything happening now is new to the material itself. The response to sustained torque under these conditions is uncertain. This does not mean collapse is imminent. Many comets survive periods of strong outgassing, but it does mean that the system has entered a more constrained state. Forces are no longer canceling out randomly. They are lining up. And when forces line up on a stressed body, the margin for error shrinks. From the outside, the orbit still looks smooth. The path through space remains predictable for now, but beneath that smooth curve is an object acting under internal thrust, shaped by jets that did not exist days earlier. The question is no longer whether 3I Atlas is active. It is whether this new level of organization can coexist with a nucleus that is still adjusting to deep internal change. Once sustained force enters the system, the discussion naturally turns inward, toward what the nucleus can actually withstand. A comet nucleus is not designed for balance. It is a fragile assembly shaped by cold, slow processes far from any star. Its strength comes from being left alone when rotation, heat, and directional thrust begin to overlap. That quiet stability is replaced by stress, and stress does not distribute evenly. Rotation is especially unforgiving. When jets apply torque in a consistent direction, they change how fast the object spins and how that spin is oriented in space. Even a small change matters when the structure is weak. Cracks that formed earlier under thermal stress can widen. Layers that once supported each other can begin to slip. What holds at one rotation rate may fail at another. 3I Atlas is already carrying the memory of extreme conditions. During its passage through the inner solar system, it experienced rapid heating followed by cooling. That cycle alone is enough to fracture material. Expansion and contraction do not reverse cleanly. They leave behind damage. Now, on top of that, sustained jets are applying torque again and again, in the same general pattern, without giving the object time to relax. This is where the analogy of drilling becomes useful, even if imperfect. Opening deeper vents is like cutting channels through a structure that was never reinforced to handle them. Each channel relieves pressure locally, but it also changes how forces move through the body. When multiple channels open at different angles, the internal load paths shift. Stress concentrates in places that were not stressed before. At first, this can make the object look more organized. Jets become cleaner. Flow becomes directional. The coma takes on structure, but organization does not mean strength. In many systems, it means the opposite. It means that forces are no longer being dissipated broadly. They are being focused. There is a critical detail that complicates this further. the spin state of 3I Atlas has not clearly stabilized. The light curve still shows uneven behavior layered with new repetition. That suggests rotation is changing even as jets become more consistent. When torque is applied to a system whose rotation is already in flux, the result is not gentle adjustment. It is strain. Some may expect obvious warning signs if failure is coming. A sudden brightening, a violent outburst, a clear split. But structural failure does not always announce itself that way. Often, it progresses quietly. Microfractures grow. Weak layers separate. Load-bearing regions thin. From the outside, activity may even look steady or improved. This is why scientists pay attention to thresholds rather than single events. There is a point at which a nucleus can no longer redistribute stress fast enough to compensate. Below that point, change leads to adaptation. Above it, change leads to fragmentation. The difficulty is that this threshold cannot be measured directly. It can only be inferred from behavior. 3I Atlas appears to be approaching that line, though it has not crossed it. The combination is what matters. Deepening heat penetration, multiple active vents, sustained directional torque, a spin state that is not fully settled. None of these alone would demand alarm. Together, they describe a system under compounding stress. There are historical examples of comets that followed a similar path. Some stabilized and survived, carrying scars but remaining intact. Others broke apart suddenly after appearing stable for days or even weeks. In hindsight, both paths showed warning signs. At the time, those signs were ambiguous, just as they are now. What makes this case different is the origin of the object. An interstellar nucleus has not been preconditioned by repeated solar encounters. It has not shed its weakest layers gradually over many orbits. Its response curve is unknown. That uncertainty widens the range of possible outcomes. At this stage, the question is not whether 3I Atlas is in danger. The question is whether it is still in a phase where adaptation can keep up with change. Every new jet, every sustained push, every additional layer of internal activity tests that balance, the object may pass through this phase intact, carrying the marks of stress as it departs, or it may reach a point where the structure can no longer respond as a whole. Nothing observed so far confirms failure, but nothing guarantees stability either. The system is tightening, forces are aligning, stress is no longer fleeting, and once stress becomes persistent, the difference between evolution and breakup depends on margins that cannot be seen, only inferred from what happens next. By this point, the range of possible futures for 3I Atlas has narrowed, but it has not collapsed into a single outcome. The data now support two broad paths forward, both grounded in known physics, and both consistent with what has been observed so far. The difference between them is not dramatic in appearance. It lies in whether the system finds balance, or whether change continues to pile on faster than the structure can absorb it. In the first path, the object completes its internal transition. The newly opened vents remain active, but they do not multiply further. The jets settle into a stable configuration. Torque becomes predictable. Rotation slows its drift and locks into a new rhythm. In this scenario, stress is redistributed rather than amplified. Cracks stop growing. Weak layers hold. The nucleus carries damage, but it remains whole. If that happens, 3I Atlas will leave the solar system altered but intact. Its coma will gradually thin as energy dissipates. Activity will decline, not because material has run out, but because the internal temperature gradient finally smooths. From a distance, the object will begin to look more like a familiar fading comet, even though its interior tells a more complex story. This outcome has precedent. Several comets have undergone periods of intense reorganization and survived. They emerged with new spin states, reshaped surfaces, and altered activity patterns. But they did not fragment. In those cases, the key factor was stabilization. Once forces stopped changing direction and magnitude, the structure had time to adjust. The second path is less forgiving. In this scenario, each new layer of internal heating activates additional vents. Jets do not replace one another. They accumulate. Torque continues to change as new forces come online. Rotation remains unsettled. Stress builds faster than it can be redistributed. The nucleus reaches a point where internal support fails. If that threshold is crossed, breakup does not need to be explosive. It can begin with separation along existing fractures. Pieces drift apart. Each fragment develops its own activity. From the outside, this may first appear as a softening of structure or a broadening of the coma. Only later does clear fragmentation become obvious. The challenge is that both paths can look similar in their early stages. A stable jet today does not guarantee stability tomorrow. A quiet light curve does not mean stress has resolved. This is why single observations are not decisive. What matters is repetition. The same features appearing again and again without major change. There are specific signs scientists watch for. Does the spiral structure persist with the same orientation and spacing? Does the secondary pulse in the light curve remain locked to the same phase? Do the non-gravitational forces stay consistent in both strength and direction? Each of these would suggest that the system has entered a stable mode, at least temporarily. The opposite signs are just as telling. A sudden shift in the spiral, a new pulse appearing in the light curve, a change in the direction of orbital push. Any of these would indicate that another internal layer has activated and altered the balance again. At that point, the clock resets. Stress accumulates further. What makes this moment unusual is the pace. These changes are unfolding on the scale of days, not months. That leaves little time for gradual adjustment. Each new observation carries more weight than it would for a typical comet. A single update can tilt the interpretation one way or the other. It is important to emphasize that neither outcome implies error or surprise in the data. Both are natural consequences of the physical processes at work. The uncertainty comes from limited precedent. Interstellar objects do not give second chances for comparison. Each one is a first of its kind in practice. Even if the underlying physics is familiar, 3I Atlas now sits in a narrow corridor between adaptation and failure. It has not shown signs of collapse. It has also not clearly stabilized. The behavior observed so far keeps both possibilities alive. That tension is not dramatic. It is quiet and technical, but it is real. From a scientific perspective, this is the most informative phase. If the object stabilizes, it will reveal how a pristine interstellar nucleus adjusts under solar stress. If it fragments, it will expose interior material and processes never observed before. Either outcome expands understanding. The only thing that is no longer likely is a simple fade into the background. 3I Atlas has already moved past that option. Whatever happens next will not be a return to simplicity. It will be the resolution of a process that has been building, layer by layer. Since the object first encountered the sun, what gives this moment its weight is not the possibility of drama, but the fact that it is happening in real time. 3I Atlas is not a relic being studied after the fact. It is a system in motion, changing day by day as it leaves the inner solar system. Every observation captures only a slice of a process that does not pause for analysis. By the time one data set is understood, the object has already moved on to its next state. This is why the language used by scientists remains careful, even restrained. Phrases like evolving coma morphology, changing volatile composition, and refined non-gravitational parameters sound neutral, almost dull, but taken together, they describe a system that is still actively transforming. Beneath that technical phrasing sits a simple reality. The processes shaping 3I Atlas have not finished their work. Cooling is what normally ends a comet's story. As distance increases, energy input drops, activity fades, structure dissolves. With 3I Atlas, that sequence has not fully begun. Heat absorbed earlier is still moving inward. New material is still responding. Jets that did not exist before are now shaping the coma and influencing motion. This is progression, not decay. The importance of this cannot be overstated. Interstellar objects offer only a brief window for direct study. They arrive without warning and leave quickly. Most are observed only in passing, their behavior reduced to snapshots. Here, scientists are watching a continuous transformation unfold, step by step, across multiple forms of data. Shape, timing, composition, and motion are all changing together. That convergence is rare. It allows researchers to test ideas as they form. When a new spiral appears, the light curve responds. When deeper spectral lines strengthen, orbital forces adjust. Cause and effect can be traced, not assumed. This is as close as planetary science comes to a live experiment. There is also a broader lesson taking shape. 3I Atlas challenges the assumption that interstellar visitors behave like familiar objects on accelerated timelines. Instead, it suggests that some may follow entirely different paths once exposed to sustained stellar heating. Their interiors may be more layered, their responses more staggered, their limits harder to predict. This matters for future encounters. As detection improves, more interstellar objects will be found. Understanding whether 3I Atlas is an outlier or an example will shape how those discoveries are interpreted. If its behavior represents a broader class of responses, then models will need to change. If it is unique, that uniqueness still teaches where assumptions break down. For now, the outcome remains open. Stabilization would show that even a pristine interstellar nucleus can adapt under stress. Finding balance before structural limits are reached. Fragmentation would reveal the opposite, that some objects carry hidden fragility that only becomes visible when pushed beyond a narrow range. Both outcomes are valuable. Neither is trivial. What is already clear is that this is not a static visitor drifting away unchanged. 3I Atlas is rewriting itself as it goes. Each layer that activates leaves a permanent mark on its structure and motion. Even if it survives intact, it will not leave the solar system as the same object that entered it. That is why continued observation matters so much. Tomorrow's data does not merely add detail. It decides between paths. If the same spiral persists, the same secondary pulse repeats, and the same directional push holds, then a new mode has likely locked in. If instead a new pattern appears, a new shift in timing, a new change in force, then the transformation is still accelerating. Either way, the process is not finished. 3I Atlas is still responding to energy it absorbed days and weeks ago. The system is still adjusting. The story is still being written, not in hindsight, but in the present. And that makes this object more than a passing curiosity. It makes it a rare chance to watch an interstellar body reveal what it truly is. Not all at once, but piece by piece, as it leaves.